geometry. We're looking at perpendiculars and distance. The first thing we're going to look at is the concept of the distance between a point and a line. So if we have this line and this point, the distance from the point to the line is implied the shortest distance. So for instance, I'm not going to say this is the distance from the point to the line, nor am I going to say this is the distance from the point to the line. Instead, I want to go in the shortest distance possible, which is the perpendicular distance. So keep that in mind. Anytime it asks for the distance between a point and a line, it's the shortest implied perpendicular distance. Next, distance between two parallel lines. So we have these two parallel lines. They stay the same distance away from each other all the time. I want the distance between them. I'm not going to go at some diagonal angle. I'm not going to go horizontal like this. Instead, we're going to go the shortest distance, which again is the perpendicular distance. And it's perpendicular to both of them. So distance between parallel lines, we have the perpendicular distance. Examples. The distance between the line y equals 3x minus 6, looks something kind of like this, and the point -1, 4. Now, we're not going to go straight vertically down. We're not going to go horizontally straight across. Instead, we are going to go perpendicular. That is going to be our shortest distance, the distance. About this red segment, I know it's perpendicular to the line y equals 3x minus 6. In other words, what I know about this line right now is that the slope of that line is -1/3. I know it goes through the point -1, 4. So I can write the equation of that line. I'll start with point slope form. So y minus y equals the slope times x minus x. And now I'll do some algebra on this. Y minus 4 is -1/3 x minus 1/3. Add 4 to both sides. Y equals -1/3 x. And if we add 4 to this, add 4 to get it off the left, add 4 onto the right, we get 3 2/3. And I prefer improper fractions, so that's going to be 11/3. That's the equation of this line. Why is that significant? Well, to find this distance that we want, it's the distance between this point, -1, 4 that I know, and this point over here. This point is on the red perpendicular segment as well as the original black line. So we want to figure out, where do those two lines intersect? Where does this line intersect that line? So we're going to set them equal to each other. 3x minus 6 equals -1/3 x plus 11/3. Set the equations of those two lines equal to each other. I don't really like having all these fractions. I'm going to multiply both sides by 3. At least for now, the fractions are gone. Then we're going to add x to both sides, add 18 to both sides, divide by 10. And so x equals 29/10. Pretty ugly fraction, but that is x value for that point. To get the y value, we can plug it into either of those equations. I'm going to choose this one. So y equals 3x, the x value that we just found, minus 6. So y equals 87/10 minus 6, which would be 60/10. If we subtract those, we get 27/10. This point is 27/10. Now, lots of little details to get to this point. Big picture, we wanted to find the distance between the point and the line. Now it turns into, what's the distance from this point to that point? And here is where we finally get to the distance formula. Big square root of x minus x squared plus y minus y squared. 29/10 plus 10/10 will be 39/10. This will be squared. And then 27/10 minus 40/10 is going to be -13/10, which has to be squared. And when you square these fractions, square the numerator and square the denominator, so we get 1521/100 plus 169/100 when we square those. We add those together, Because they have the common denominator, we get square root of 1690 divided by 100. Now about simplifying this, I guess I could divide them both by 10. The numerator would be square root of 169, which is perfect. It's 13. And it's over the square root of 10. I don't want this square root in the denominator, so one more step. Multiply numerator and denominator by square root of 10. So 13 root 10 over 10 is the distance. It's the distance from the point we were given, going the shortest possible distance to the line that we were given. Here's another example of finding the distance between a point and a line, and all these calculations are worked out. You can follow this work just like the last one. Another type of problem we're going to see is to find the distance between two parallel lines. And I'm going to make a quick sketch of this. First of all, y equals 3x minus 6 will look something kind of like this. And y equals 3x plus 2 has a bigger y-intercept, so it'll be a little bit higher. It's going to look something like this. Now, I could find the distance between any of these green segments, and that would represent the distance between the two lines. Any one of them would work because all of those are the same. However, I'm not just going to pick any segment. I'm going to pick a strategic one. I should go from either this y-intercept over to that blue line, or from this y-intercept down to that red line. And my drawings aren't terribly precise because I don't know if this is actually an x-intercept to the red, but I am intentionally coming from this y-intercept of the blue line, so that point is 0, 2, and I know that. And then to find the equation of this segment, we know it's perpendicular to those two lines, so the slope perpendicular is going to be negative 1/3. I know it goes through the point 0, 2, right, because it goes through that y-intercept. So the equation of that line is y equals negative 1/3 x plus 2. That is the equation of this green line. Now, why is that significant? Well, if we can find the distance from 0 to perpendicular over to this point, then we have our distance. I do not want to say, well, the distance between 0, 2 and 0, negative 6, the distance between those two y-intercepts is a distance of 8, because that's not the shortest distance. Instead, we want to find the distance between this point and that point. Now, where does this green line intersect that red line? We'll set them equal to each other. 3x minus 6 is equal to negative 1/3 x plus 2. And multiply everything by 3. 9x minus 18 equals negative x plus 6. Add x to both sides. Add 18 to both sides. Divide by 20, or divide by 10. So x equals 12/5. It's on the red line and the green line. The red line has nicer numbers to work with, so if I use that equation, y equals 3 times 5 minus 6, so y equals 36 over 5 minus 6 would be 30 over 5, so y equals 6/5. So if we can find the distance between those 2 points, that's going to be the perpendicular distance between those 2 lines. So distance formula, 12/5 minus 0 squared plus 6/5 minus 2 squared. So 12 over 5 squared. 6 over 5 minus 10 over 5 would be negative 4 over 5 squared. When we square those, square the numerator and the denominator, so that's 144 over 25. This is 16 over 25, so it's the square root of 160 over 25. Now to break these down individually, the square root of the denominator is plain old regular 5. The numerator is the square root of 16 times the square root of 10, so how about 4 root 10? And then that would be the distance between those 2 points, or any 2 points that are perpendicular to each other on those parallel lines. To go down a little further, this next example also goes through the same type of problem. You can see my worked out solution for that one. There's also a video link in OneNote where you can look at additional problems of finding the distance between parallel lines. Number 5 is the same type, and if you look back in OneNote later, I'll have this one worked out. instead of the distance between a point and a line, you'd have to find the equation of this line first. And then it's a lot like problem number 1. As far as other things from this unit, we have what's called this dual parallel theorem, which says that, graph of this one, if we have two lines, like this black line and this black line, both of these black lines are parallel to this blue line. So the top and middle are parallel, L is parallel to M, K is parallel to M, then we can say that L and K must be parallel to each other. So quick proof of that. 1, 2, and 3. If M and K are parallel to each other, that means measure of 2 equals measure of 3. If L and M are parallel to each other, it means measure of 1 equals measure of 2. So then through a transitive property, the measure of 1 equals measure of 3. And because these corresponding angles are equal, it means that those lines are parallel to each other. Perpendicular transversal theorem. So if I have line P perpendicular to line P, and we have to make the note here that this has to be in the same plane, whereas this one could be three-dimensional, and the dual parallel theorem is still going to work. So if T is perpendicular to P, and if P is parallel to Q, so here is line Q. If these are parallel, the first ones are perpendicular, then what we could say is that T is perpendicular to Q. So theorem true. This perpendicular transversal converse is more significant. And it says that as long as we're in one plane, if P is perpendicular to T and Q is perpendicular to T, so if this is a right angle and this is a right angle, then what we can conclude is that line P is parallel to line Q. And last one, we have an argument to make here. Given that measure of angle 1 is equal to the measure of angle 2, given that angles 6 and 2 are supplementary, we want to prove that measure of angle 4 is equal to the measure of angle 5. So because it was given that measure of 1 equals measure of angle 2, we could say that, kind of hard to read these letters, but line L is parallel to line I, L parallel to I, and the reason for that is since those alternate exterior angles are equal, the lines are parallel, or you could say the alternate exterior angle converse. Because those angles are equal, it means these lines are parallel to each other. Next, because 2 and 6 are supplementary to each other. If I look at their location, they're same side interior angles. So now I can say that line I is parallel to line N. This line in the middle is parallel to this one because the consecutive interior angles being supplementary means the lines are parallel. Or you could say that the consecutive interior angle converse. All right, so now, since L is parallel to I, N is parallel to I, we could say that bringing these two things together, organize my work very well here, I can say that L is parallel to N, and the reason for that is that dual parallel theorem. Two lines like L and N are both parallel to the same line, like parallel to I, and those two lines are parallel to each other. All right, well, now that L is parallel to N, I can look at angles 4 and 5. Based off of their location, they're alternate exterior angles. So I could say that measure of 4 is equal to the measure of 5 because parallel implies that alternate exterior are equal. Or we could call that the alternate exterior angle theorem. Not the converse. The converse is when we're saying because those angles are equal, 1 and 2, that means that those lines are parallel. Now we're saying, now that we know that these lines are parallel to each other, we can say that the angles are equal to each other. And that is a pretty good argument as to why 4 would have to be equal to 5. Last thing, find K so that the line passing through these 2 points is perpendicular to the line containing those 2 points. Well, as soon as I heard perpendicular, I thought slope. The slope between those 2 points, -6 minus 2 over 1 minus 5, that would be -8 over -4, or 2. And if it's perpendicular to this one, it means the perpendicular slope we're looking at is -1/2. So let's go ahead and calculate the slope between those 2 points. So the actual calculated slope, k minus 0 over 15 minus 3, simplifies a little bit to k over 12. and that's supposed to be equal to this negative 1/2. Algebraically, because fraction equals fraction, we can cross multiply. 2 times k equals 12 times negative 1. Divide both sides by 2, and so k equals negative 6.